Algebra 2, Chapter 9.1, Inverse Variation. Essential question, what does it mean for one variable to vary inversely as another variable? And at the beginning of the course, we worked through parent functions of Algebra 2, one of which was the inverse function, which is going to be y equals 1 over x. And so this is the type of parent function we're looking at from which we're going to derive these real-world uses. So it's kind of an interesting situation. So we're going to start out going with this Explorer, investigating inverse variation. And here you have a graph of how, if you have a formula, area equals length times width, and that given a fixed width, the area of this rectangle depends on the length of the rectangle. So if length is 1, width has to be 2. So anyway, your area will vary directly. Now, what we're going to do is explore and see what happens to the length and width of a rectangle if we hold an area constant. So we're going to go to the next page. So we have let the area of a rectangle be 12 square units. Complete the table, which lists possible positive integer lengths and widths for the rectangle. And so for an area of 12, 1 times what equals 12? Well, that's going to be 1 times 12, so it just starts the table. So what times 2 is going to produce an area, a rectangle with an area of 12? Well, 2 times 6. And then what times 3 equals 12? 4. What times 4 equals 12? 3. What times 6 equals 12? 2. And what times 12 equals 12? 1. So that's what that looks like. Now, be on the coordinate plane shown, draw each of the rectangles having the lengths and widths in the table from step A. Well, the first one is given to us. We have a width of 12 right up here, this one at the very top. We had a width of 12 and a length of 1. And so that's going to go right up here. And then next, we have a length of 2 and a width of 12. So a length of 2 and a width of, width of 6. 12. So we have this rectangle right here. So let's draw the rectangle. So here's the rectangle associated with length of 2, width of 12. Next we have length of 3, width of 4. So this rectangle right here. Okay. Next we have length of 4, width of 3. So here's this rectangle. Next we have length of 6, width of 2. So each of these rectangles that I'm drawing has the same area. So the area is constant. Next, and the last one, a length of 12 is going to be width of 1. So write an equation that gives W in terms of L. Well, algebraically, we have area equals length times W. And if we want W in terms of L, what do we have to do? Well, if we divide both sides by L, we get W equals area divided by length. So that would be an equation. Okay, formulating, and here we have explain one gets to kind of the parent function in essence. We have y equals a over x, where a is called the constant of variation. Well, in the parent function that we saw earlier, y equals 1 over x, the constant of variation is 1. And then we have end behavior. This is a real world. It's a quadrant 1, totally quadrant 1 function. As x approaches 0, so as x goes to the left, what does y do? Y approaches positive infinity. As x approaches positive infinity, y approaches 0. Okay, we go, x goes to the right, y approaches 0. And so there are different ways of rewriting this function. Now, this is analogous to this xy equals a. It's analogous to, in our example earlier, width times length equals area. Okay, so area in the case of the rectangles situation was our constant variation. And this there are a lot of real world uses for this. I had a friend of mine, Craig, who wanted to get some friends together to watch a prize fight. I'm not a big fan of paying to watch people beat each other up, but I think the cost of the fight was, I forget exactly what it was, but it was maybe $100. And so with 20 friends there, we each had to pay $5. And what you had is a situation where if this, depending on what the number was, if we only had 10 friends, our average cost would have been $10 a person, and it would have changed. And so what you have is 100 becomes your constant of variation, and your variables become these other two numbers here. So that's kind of what we're looking at here. Just like we take area, our area of 12. Okay, so 12 was equal to our width times our length, and that if we keep the 12 fixed, which is our constant variation, that's going to impact the relationship between the width and the length. Okay, let's go ahead to this one. We write an equation relating the variables and use it to answer the question. The time, t in days, takes theater crew to set up stage for a musical varies inversely as the number of workers, W. If 30 workers accept stage in 4 days, how many days would it take if only 24 workers were available? Now, first of all, it really helps to think. So if it takes 30 workers 4 days to set up the stage, if you only had 24 workers, would it take more time or less time? What does common sense tell you? Well, common sense should tell you that it's going to take more time. So just kind of try to think. That can help you get through situations. So write the general equation. So we have, here's t, time equals a, which is our constant variation divided by number of workers. Okay, so substitute the known values. So time, which is 4 hours, equals our constant variation over 30. And then if you cross multiply the 30 to the other side of this equation, you're going to get 4 times 30, or 120, is equal to A. So A is our constant variation. So here's our equation. What I like to do is you can just substitute in. So if you want to try 24 hours, you can take 24 in the place of the number of workers, and now what you have is you'll get 120 divided by 24, or 5. So 24 workers can set up the stage in 5 days. Now, earlier, just kind of thinking, trying to be logical about it, we knew it was going to be more than it would take 30 workers to set up the stage. Next, the time t in hours it takes a group of volunteers to clean up a city park varies inversely as the number of volunteers v. If 10 volunteers can clean up the park in 6 hours, how many volunteers would be needed to clean up the park in 4 hours? So here we have, write the general equation t equals a over v, and basically we're going to plug in numbers for t and v, and it says substitute known values. Well, we have 10 volunteers in 6 hours, so here it says substitute known values 10 equals a over. No, it's not 10, guys. That's t. T is going to be 6 hours. And then it takes 10 volunteers. And so if we solve for a and cross multiply, we're going to get 60 is equal to a. So the equation is t equals 60 over v. And now using the equivalent equation, vt equals, because if we cross multiply the v, I'm just going to go right here, we get vt equals 60 right? So vt equals 60. We substitute 4 for t and solve for v. So v equals, no, v times 4, v times 4, right? We're substituting in for t, equals 60. So if we divide by 4, we'll just work to the right here. V is going to be equal to 60 divided by 4, which is 15. So whereas it took 10 volunteers to clean up the park in 6 hours, it's going to take 15 workers to clean up the park in 4 hours. So we get V equals 15, and so 15 volunteers are needed. So that's as far as we're going to go today in this, and we're going to have some exercise in the next video related to this. This shouldn't be too hard. Good luck, and thanks for viewing.